Welcome to Virtual FOSDEM and welcome to the session about running MySQL NDB cluster in Kubernetes. And yes, in case you had any doubts, I will show you. Sure, you can run your database on MySQL NDB cluster in Kubernetes without any problems. My name is Bernd Ocklin and I'm running the MySQL NDB engineering team at Oracle. Today I'm presenting here from my hometown Stockholm, where we also have a small office that we share with some of the Java folks at Oracle. First of all, I want to briefly introduce you and walk through some aspects of both technologies, cluster and Kubernetes, but also assume that you have some basic understanding of both of them already. So, what is MySQL Cluster to start out with? MySQL Cluster is a sharded distributed database. It is designed to be highly available. It is always consistent across the entire sharded distributed data set, which is very important, because it makes programming so much easier when the data set that is distributed actually from the application perspective looks as if it comes from a single instance database. MySQL Cluster is massively linearly scalable, has a shared nothing architecture, and is obviously open source. MySQL Cluster, as already mentioned, is very much used in the telecom industry, but also in gaming, where massive parallel online games need a session store. It is used also for financial transactions in the financial industry for online payment providers. Particularly telecom is now moving towards cloud native and Kubernetes in light speed. They were a heavy adopter of OpenStack in the past and now aggressively move on. They like the speed in which you can introduce new services with Kubernetes, the scaling, the efficient operations, the performance and capacity it provides. Very often I get doubts about running databases in containers or in Kubernetes. We have been running databases and MySQL NDB specifically on virtual machines for ages, right? We do most of our testing there. Huge cluster installations run in virtual machines and in production. And containers in Kubernetes have so many advantages over virtual machines that I think, yes, many databases and specifically MySQL NDB is very well suitable to run in Kubernetes. So if you want to compare virtual machines versus containers, I think it's a clear win for containers. But there's a couple of things that we still have to work on and that we have to consider. For example, workload isolation. I think virtual machines isolate workload much better if configured correctly, but we have also seen overutilized systems there that cause problems. And then maybe another point to make is best practices. I think we still understand virtual machines and the behavior of our databases or services in general in machines, virtual machines, a little bit better. There's more best practices built up, and there's still a lot to learn for containers. But Kubernetes is moving quickly, and we see new information, new blocks, and gain new experiences every day about running them there, now that we have huge systems in production. So running databases in a container and Kubernetes, and I think, yes, in the end, you can run any database in a container, period. But it's a matter of workload that you want to serve and the requirements that you have on a database. So mileage varies pretty much with the database suitability. What does make a database suitable for cloud-native principles and also for running in Kubernetes? I think the most important thing to highlight is resilience. So losing parts of the system, of the database system, should be a non-event. It's not a big deal. It should automatically recover and heal itself. Shared nothing. You should not have anything, no centralized management or any single point of failure in the system, in your database system, if you want to run it in Kubernetes and adhere to the cloud-native principles. Scaling, sharding, scale out, not up. Consistency. So a database should look like a single machine system to the user and to the services. That makes life so much easier, and it should be consistent. And the data should be served independent of the instance that you go to in order to query the data. Standards are also very important. Cloud-native databases should also support query standards as much as I like the idea of NoSQL that we also implement in MySQL NDB cluster. But there should always be a standard way of accessing your data so that you can swap out your database and do not entirely depend on a single vendor. So if you look at the cloud-native databases, like a classical old RDBMS, it cannot score on any of those. Maybe they are a little bit better usually on standard query languages, much more mature there, but otherwise they don't score anywhere. And then MySQL NDB cluster, it really has everything that you need to run in Kubernetes. And I think MySQL NDB cluster is a true cloud-native database in that sense. So when we talk about cloud-native and we talk about Kubernetes specifically, we talk a lot about stateless. And I always wonder, what stateless? Stateless, can you write an application without state? No, you have some state always, anywhere in the system. But this is not about, when we talk about stateless in Kubernetes, we don't talk about really to avoid any state at all, which is impossible. You should design components in a way that they're stateless whenever you can make them stateless. So it's not really about stateless, but about being smart about the state and making applications state optimized. So let's look now at Kubernetes and the Kubernetes environment that we are in when we want to run a database in Kubernetes. So for me, Kubernetes is pretty much this environment that we are moving in. We have an infrastructure that consists of Kubernetes itself, the Kubernetes cluster, and Docker. Then we have platform services. Those are the services that you typically need in order to run your application or services in Kubernetes. You have metrics by Prometheus, or you have Envoy as a proxy. Then we have your application, the microservices, and the data layer, where you can store the state for those microservices. We talked about that earlier. I wrote again stateless, but what I mean is state-optimized services. And then we have all the orchestration, automation, and analytics and reporting. So all of this is your Kubernetes environment, and that's the environment that we want to run MySQL cluster in. Kubernetes consists of objects and resources, and those you need in order to run the database. But first we have the containers. Those we just simply pull in from Docker Hub, take the official containers from there, and run them. So multiple containers are running inside the pod. So pod is like the most minimal entity in Kubernetes. And pods are being scheduled on Kubernetes nodes. You can have multiple pods obviously running, and typically multiple pods are being managed by workload resources via the workload API. And so if you want to run a database like cluster in Kubernetes, we would use stateful sets, because only stateful sets, unlike deployments, they provide a unique network identifier, a stable one, so that you always have the same host name for the same pod that you run your data nodes in, your MySQL database instances. Then it provides also stable persistent storage, which is quite important for a database, because you want to, if the pod is rescheduled to another node, you want to actually be mounted to the same persistent storage in order to recover your data from there. In order to provide a network identity for the pod, you need a headless service. Configuration. In order to configure your database, you would use config maps. And you don't have to, but you can mount the data that is inside the config map in order to configure your database as a volume in the containers. So they are accessible like a file, which makes it very easy for older databases to retrieve config information from outside via the config map. And then last but not least, you obviously want to store your data somewhere, your tablespace files, your redo log files, and so on. And those you store in persistent volumes via persistent volume claims. So here in this picture, we have already all the objects and resources that you would typically need in order to run a database in Kubernetes. Let's briefly look at the cluster architecture and map then that to running cluster in Kubernetes. So here, cluster is very simple, right? We have stateless microservices, your application that you want to run. We have an optional SQL layer in order to access data in MySQL cluster with standard SQL. And then we have cluster itself. That's data nodes, distributed, partitioned data in the network. If we want to map that and run cluster in Kubernetes, we take the data nodes and they are running in a pod. The pod accesses the system volume in order to write data to it or read data from it if necessary. We add a little sidecar container that we get to later on. And we have the configuration that we are reading with the management server and then as a configuration provides centrally to the data nodes. So I've said earlier, cloud native and central doesn't really fit together, but don't be worried. The management nodes are just really only there in order to read the configuration and provide it to the data nodes. They are not involved in any kind of data management. And then they are also not a single point of failure because there should always be two management servers. So if we put all those pieces together, we see how you can actually fit MySQL cluster into Kubernetes. So we have the Kubernetes cluster, we have the MySQL servers, we have the stateful sets with the pods, with the data nodes, and the stateful sets with the management server. And then we have kubectl or whatever client in order to access and manage MySQL cluster there and the Kubernetes objects. I will now show briefly how to deploy all those files manually that are needed in order to create MySQL NDB cluster in Kubernetes. For that purpose, let's have a brief, quick look at what kind of files we have. So there's the config map, we have the persistent volume claim that we need in order to provide the persistent volume to the stateful sets that are running the data nodes and the management server. We have the services that are needed to give the network identity to the stateful sets and the pods running in them. And then we have the file to create the stateful sets, for both the management server and the data nodes, NDB. And then we have pretty much the same thing as a preparation for MySQL, like the config file, config map, PVC for MySQL server, and then a service as well. But in this case, we create MySQL with the deployment. The content of those files you have already seen in earlier slides, so I don't go into those details. So we start out with starting a plain vanilla Minikube cluster here. Then now that's started, and then we start the tunnel as the next one. So the tunnel is there in order to expose the external services, the load balancer services that allow us then later to access components inside the Kubernetes cluster from outside. And now we are going to a new terminal window and create first the config map. That's quite quick. Then persistent volume claim. Then the service. So let's check briefly back on the Minikube tunnel output. There's the external load balancer service as well. Okay, then now we can deploy the management server. So since I created the load balancer service, we can now access the management server console through that load balancer service. Let's check. There's all the configured nodes and a running MySQL management server for NDB. So now let's start the data node. Use the management console again, and there we have the data node as well. Next step is to prepare the services, config, maps and volumes for the MySQL server. I do this in one preparational step. Now start the MySQL server, go to the console again and see MySQL server is there as well. And in the interest of time, I don't play with the cluster anymore. But you can download the files from GitHub and try yourself. Okay, let's talk more about best practices. So this is about things that we collected in the field when running production systems in Kubernetes. And best practices we collected when writing our NDB operator, which hopefully soon will be released in the first version. So the first thing that we hit is DNS stability. And what I mean with DNS stability is that pods can always be rescheduled on new Kubernetes nodes, and that can always change IP addresses if they are being restarted. And then if you consider now DNS time to live, it can be a hassle to resolve host names in those kind of networks with permanently changing IP addresses of components. I mean, the first obvious thing is that you shouldn't be using grant in order grant privileges to a user for a certain IP address in your database, because that will never work because the IP address will change. But it's also about components finding each other, because the host names that they're looking for might temporarily be unresolvable. So you have to do retry until it then again receives a new IP address from the DNS for the component you're actually using. Then another one is service mesh issue. For example, if you want to run encrypted links between the Kubernetes pods or containers, then Envoy is a proxy that can be used for that. And the problem is with the proxy that the connects, even though they come from a remote system, actually look like they're coming from localhost. But Cluster expects a connection from a remote host and by default would reject them. So you can use this parameter here, TCP bind in address any equals 1, in order to avoid this expecting a connection from a remote host instead from a local host. Then maintenance of containers in a pod can be a little bit of a hassle. So I think a very classical pattern in Kubernetes is to run a minimal maintenance sidecar container. It's usually idle, doesn't do anything, but it allows you to parallelly access the volumes and the data stored in them in case there's anything going wrong in your main application container or database node container. This makes debugging so much easier if things go wrong and pods are starting over and over again with you without you getting any access to the log files. Then these come in very, very handy. One thing that I generally want to mention is that Kubernetes is very complex, right? I mean, there's many teams and layers involved and teams that are responsible for those layers. And there's lots of people and resources to blame if something goes wrong. And so observability is key so that you know what's going on inside your cluster. And we just last week had, for example, an issue where cluster was crashing all the time. It was a production setup and we didn't know what the problem was until we, with the involvement of many teams and people, tracked it down to the actual firmware on one of the Kubernetes nodes that was omitting to acknowledge and send an acknowledgement to network packages. So pretty much network was completely going corrupt and we couldn't run cluster stable on it, but it took the involvement of many, many people and teams in order to resolve the issue and track it down. So eviction API is something you should be familiar with because it's something that you use when you want to drain Kubernetes nodes from the pods that are running on them. And this eviction API considers pod disruption budgets, because one thing you don't want to happen is when you drain Kubernetes nodes that you accidentally actually shut down your database because you have been removing or have been evicting all of the last remaining nodes of your database. And so define a pod disruption budget with labels, and then you go. Unfortunately, kube delete, for example, ignores pod disruption budgets. So if somebody goes in manually with a kube delete, then you still could be in trouble, but it's at least a good insurance in order to keep your database as safe as possible. Yet another thing is pod affinity and anti-affinity. So as I already said, all pods should have labels and make heavy use of those labels. And pod affinity allows you now, for example, to do things like schedule pods for that run database parts that share the same data on different machines, in different availability domains, different racks, so that things that should not run together on the same hardware can actually be kept apart and run on different Kubernetes nodes and on different hardware. But it's also good in order to make sure that, for example, you run and find faster storage in the Kubernetes cluster by looking for labels that you agreed on that mark SSDs, for example. So all port affinity and anti-affinity is extremely important in order to run a distributed database in the safest possible way and make it highly available. There's many more things I would like to share, but I think time's otherwise running away, and we should go to the next. Kubernetes operators, they use, like everything else in Kubernetes, a declarative approach. That means you describe the state of the system that you want to get to. Then the idea of an operator is, even though it's software, it's supposed to service and manage your services like a human. Operators are based on custom resource definitions. So like we have stateful sets and pods and config maps, they're custom resource definitions that you can define and where you can define the schema in order to describe the state of your service and your application that you want to get to. And based on those custom resource definitions, then the operator is taking action and driving the system towards the desired state. We have looked at the picture already earlier, the components of running MySQL NDB cluster in Kubernetes, and I added here the operator and the operator with the MySQL controller, with an NDB controller and backup, restore controllers, all this kind of parts that you would need in the system and all this kind of tasks that also a human operator would be doing on a service are being reflected here in this operator. And these are the components of it. Now I want to show the operator demo. We started with the custom resource definition, and as you can see, just only one file, much simpler. And with that one, we configure an example cluster, take a standard image from a Docker Hub. We define 2 nodes, one at a redundancy level of 2. That means that we will be having 2 data nodes that are completely mirrored. And we want to also create 2 MySQL servers. So I already started the fresh Minikube here. Then via Helm, I deploy new necessary RBACs and our NDB custom resource definition for the operator. So the RBACs are necessary to provide privileges to services running inside the Kubernetes cluster. I start the operator out of cluster for the ease of it. Could also start it inside cluster. So lots of messages, as you can see, log messages. As I run this in background, I can now try to deploy the custom resource definition in the same shell and define cluster and the state of cluster, what I think it should look like. So the file that we have seen earlier. See what happens. Lots of messages again. So if we go quickly back to Minikube tunnel, then we will also see the external services created there. So the operator seems to be finished now, shows that all the resources exist. Pod state is also logged here, a little bit verbose maybe. And then we see that it has driven cluster to the last config version. In this case, it's config generation 1. So if we go to a third window, we can briefly see what kind of pods are created here. See the name, stateful set pods with clear names and ordinal numbers, then the MySQL server in deployments with just the random pod names, and briefly connect to the management console to cluster again, shows status, and here we see, voila, 2 data nodes, 2 management server, and 2 MySQL Ds. With that one, I think I'm closing the demo. That's it from me for today, for the session at FOSDEM, at the virtual FOSDEM. Thank you very much for listening. I hope you learned something new, and it was interesting. Thank you very much, and talk to you later.